Hi everyone, and welcome to today's webinar, which is Peregrine Structural Layout Optimization for Grasshopper. I'm Tom Pritchard. I'm the Peregrine Product Manager here at Limit State, and I'll be your presenter for today. Just briefly before we get going, just to say that we will, hopefully at the end of it, have time for a bit of a Q&A. So if you do have any questions that arise during the webinar, then do please type them into the interface and I'll try and get round to them if I can. If we don't, then I'll make sure that we do follow up everything via email afterwards. So to get on with it, let's look at the overview. So we're going to take a brief look at the benefits of structural optimization and then the key applications of Peregrine optimization, including holistic conceptual design of buildings, optimized structures that include cables, ensuring symmetry in the design, and also the stability of optimal structures. And then at the end we'll summarize, and like I said, if we have time, we'll get into the Q&A as well. So for the benefits of structural optimization, they depend somewhat on the objectives, but one of the drivers is undoubtedly the climate emergency. So a drive to get more from the same amounts of material. And in construction industry, we know that material usage and the corresponding CO2 emissions are a problem. So concrete, steel, and to some extent aluminium are responsible for almost a quarter of our annual CO2 emissions. So anything that we can do to reduce that, including structural optimization, would make a big difference. So how do we do that? We can build less frequently, we can reuse more than we do currently, and where we need to build new structures, we can use optimization such as you would find in Peregrine, in order to get the most benefit from the materials that we are using. So the focus here at Limit State has been on layout optimization for a number of years. It's a less widely appreciated approach than maybe other forms of optimization. So you may have all seen the organic shapes that you get from topological optimization, especially in the 3D printing area. But what we're looking at here is layout of discrete, or should I say, sort of elements between points rather than necessarily the organic structures, like I say. So here on screen we've got this truss example, and at the top we can see we have a traditional Pratt layout, and that's what we would generally look at as a standard design for this type of problem. But on the bottom we have a layout optimized structure, and that uses 40% less volume of materials for exactly the same deflection limit. So we can see that there's a massive reduction in material usage just by being able to modify the layout of members in an intelligent way. So that's what layout optimization can and does do for truss design. Another opportunity is in beam grillages in buildings. So again, at the top here, we can see our standard design where we have an orthogonal beam for the floor plate with a ring around the outside and smaller elements in the middle, and we can significantly reduce the material usage if we're prepared to change the way that we actually think about the layout. So as I say, standard design is orthogonal with these uniform prismatic beams, and using layout optimization we can modify both the direction and allow variations in beam cross section to bring about massive savings. Here almost a 3/4 volume reduction, so 74% lower than the standard design that's using prismatic beams. So we can see quite easily that there are very significant reductions that are possible if we embrace new technologies such as layout optimization and the applications that contain those. One of those applications is Peregrine. So it's a structural layout optimization tool within the Grasshopper Rhino 3D parametric modeling environment. And it's a tool for conceptual design for frame structures with applications, as we've seen in the structural engineering and design for additive manufacturing sectors. And the good thing about it being within Grasshopper and this parametric modeling environment, which we'll see in a minute, is that you can make very quick on the fly changes to different parameters and see what effects that has on your structure. And Peregrine's been out for a while, and there's a number of examples of the application being used to develop designs for real-life use cases. On the left here, we can see a pipe gantry that's been designed by Arup. It's perhaps not the most high-profile or sexy of applications, but where optimization of a standard design can be rolled out and help to save materials through repetition. You can imagine the same process being applied to pylons, cranes, off-the-shelf cantilever roof designs and the like. Each of those will contribute to a much larger global material saving and help drive down the impact of new construction. On the right here, we have perhaps the other side of the coin, which is a bespoke cantilever truss design that's been constructed using metal additive manufacture or 3D printing. The layout here having been optimized for both the specific end application and the manufacturing process. So just in case you can't make it out, the truss structure is here, and the printer is actually a welding arm on the end of a robot arm. And that's been undertaken by MX3D. And what we're hoping is to see over the years many more examples like this. And if you have some yourself, then please do let us know if you're using Peregrine and have something you'd like to share. We're always very interested to hear about those. So we'll take a look at the applications and features of Peregrine. First off, a little bit about the workflow for those of you who might not be familiar with optimization, especially optimization using Peregrine. Within the parametric modeling environment of Grasshopper, it's a relatively linear workflow for Peregrine to undertake an optimization. So first, we define the problem by specifying our allowable design domain, materials, supports, and loading. Once we have that in place, we're in a position to carry out our initial layout optimization. So in the previous slides, you'll have seen the results of that. And this provides us with a baseline volume and a starting point for any downstream operations. And those operations are generally to post-process the results in order to refine the design for perhaps a number of practical considerations. So for instance, you can use what we call a geometry optimization to relocate the joints in the structure and also potentially combine members in order to simplify the results that you get while at the same time increasing the efficiency further. And there are other post-processing stages that one can undertake, for instance, to ensure structural stability or to filter out members that are perhaps smaller than desirable for your particular end application. And we'll touch on those a little in a minute. And finally, once you've got a satisfactory design, you can output that to query the structural details and also look at the optimized form on the screen. And for anybody who's interested in taking a deeper dive into how layout optimization itself works, you can check out one of the earlier Peregrine webinars that's available on our YouTube channel. And once this is up and posted, I'll add a link to this and also in the description of the video. So a little bit about the applications and features. Some of the powerful features of Peregrine are the ones we're going to look at today. So firstly, holistic building design, including those beam grillages that we talked about previously, tools for cable stayed structures, mirroring loads and supports and sort of how that can benefit us, and also global stabilization. So first off, let's take a look at building structures and specifically grillages and holistic design. The benefits of being able to optimize a building structure in the whole is perhaps best demonstrated by this example here of a simple brace tower. And this is a problem that was examined by one of my colleagues, Dr. Lin Wei-He, as part of the development of the algorithms that underlie the grillage optimization functionality in Peregrine. And we can see from above, we have a floor plan that's subject to wind load in 4 directions. And from the side, we have 10 stories subject to gravity loading on the floors. And it's useful for us to be able to optimize these simultaneously. So what we have, or what we're looking for, is a brace 10-story building on a 10 by 10 meter footprint with a 5 meter story height. During the development of Peregrine, we compared various design schemes from fully optimized through to simple hand calculation type designs. And rather than designing in a piecemeal fashion and maybe iterating towards an acceptable outcome, what we want to be doing is being able to consider everything together. So what we're saying is we use this holistic design to simultaneously optimize both the cross bracing that we're getting, the grillages for the floor plates themselves, and the column positions and sizing. And the benefits of this are that each part of the structure knows about the others and can consider the forces that are transferred between them during the optimization, allowing the best outcome possible to be identified, rather than, like I said, designing each part one by one and then trying to work out how they interact with each other. And just because the time available, we'll look at the two extremes here to highlight the benefits of it. So first off is the hand type calculation, and this is the solution you get generally if you just design this by hand. We use this as a benchmark, and it's a simplified orthogonal grillage, as we see here on the right, with 45-degree cross bracing between floors. And if we use that as our benchmark, our volume we can set 100%. But what happens when we let Peregrine optimize the entire scheme without any restrictions on the member geometry or positions either for the grillages or for the bracing? Well, the solution's shown here, and the headline is the volume is under 1/3 of the volume of the benchmark structure. And how's that been achieved? Well, that's been achieved in two ways. Firstly, by the presence of what we would call a Mitchell truss type bracing between the floors. So you can see that faintly in black in the background there. And also, perhaps more strikingly, is by changing the orientation and the layout of these grillages. So now it's spun from being orthogonal to being at 45 degrees with these non-prismatic cross sections, as we can see here. And so one might argue that this design is potentially much more complicated to construct. However, with these particular magnitudes of material savings and the ability to use the parametric design features of Peregrine to then further modify the design to best fit the targets that you're after, the possibilities of the method, I think, are quite undeniable. So I think that's enough presentation. We'll jump into the software. So if I bring it up here, what we can see here is a problem that's using the grillage domain component in Peregrine, and actually it's available within the example files that are shipped with the software, and you can solve it for yourself during the trial period that you get with it. And the problem's one of a residential tower block along with two-story commercial space below that covers a wider footprint, and the loading as previously comes from gravity loading on these floor plates, as well as wind loading, in this case coming from sort of northeast to southwest on the thing. Again, the general workflow is the same. So we can see here on the left hand side of the screen a zoomed out view of the Grasshopper canvas, and it's setting up, solving, refining, and then looking at the output. So the interesting things to look at here are the design domains. We can see here at the top, we have one that defines the grillages for the base, one that defines the grillages for each floor of the tower, others that define the cross bracing in the walls. So we can see here in light blue to sort of denote glass, and then a final 1D domain that represents all of the columns. And each of these has an associated geometry, an associated material, and associated support conditions in the case of the columns. Everything else doesn't actually have support. It's all driven through the columns down to the ground. As this problem is actually reasonably complex, given that it's got several load cases and several types of domain in it, I won't actually solve it on screen because that would take maybe 30-40 seconds. So what I've done to save you the wait is actually solve this problem in advance and hidden the output. But if I join up the solution data here from our layout optimization into the display, we can see the results of the optimization on screen. So if we look at it from above, we can see an interesting layout for the grillages, which is different for both the commercial floor plates and the residential floor plates. And then if we take a further look here, we can see that the cross bracing has been introduced only in the areas where it's absolutely necessary in order to provide stability. And also the columns are of different cross section depending on where they are in the structure. And I think if I come around to this corner here, we can see actually there's some column locations towards some of the corners where actually that cross section has reduced to 0. So it's saying, okay, we don't actually need any columns in those positions. And just to reiterate, this is a holistic building design, so all of the different components know about the forces that are being transferred from the other components, and everything has been optimized at the same time. So we know that we're getting the best solution possible from this. So that's briefly touching on grillages and holistic design in Peregrine. The next thing we're going to look at is cable supported structures. So in a basic optimization problem in Peregrine, the self-weight is lumped at the nodes and neglects bending. But what we can do is add catenary members to the optimization by allowing them to carry axial stresses only under a combination of axial force and self-weight. And alongside that, we've also implemented rigid and pin jointed beam elements with a degree of bending strength allowable in them in order to determine whether the best structural element between any 2 points is a pin jointed member, a rigid member, or a catenary element. And that opens up the field to consider different core structural types as part of the optimization process. And all of this is covered in a very nice paper by Fairclough et al. That's in the Proceedings of the Royal Society. So do seek that out if you're interested in the methodology that's behind the cable supported structures in Peregrine. So again, what we'll do is we'll just leap into the software. So I'll close this. And we'll take a look now at this problem here. And we can see this is actually a stadium example. If we look at the top level again, the workflow is very much defining the problem, solving the problem, and then either refining the output or looking at what the final solution actually is. And here, the red part is our design domain, and we're actually mirroring it in a circle or having it as a circular array in order to ensure symmetry in the problem. So if I go in and solve this, so you can see here, just toggle on. What we've got is a ring around the outside and cantilever trusses coming into the center of our stadium here. And we can see, actually I probably should have mentioned this earlier. At the moment, we have one material defined in it, and that's effectively steel that is equal in tension and compression. So we can see our self-weight model is lumped. We also have up here defined a catenary self-weight material with a tensile stress of 1000 and a compressive stress of 0. If I now join that up and allow it to be used in the structure, we can see that then the form of the structure has changed quite dramatically. So we still have this outer ring, but instead of these cantilevers coming into the middle that are acting as trusses, we've actually got these cable structures. and further rings towards the center of the structure. If I then look at the post-processing, we can actually turn on simplification to see what effect that has, and actually it's taken out some of the smaller elements towards the center of the structure there. But one of the interesting things we can perhaps do is change that tensile stress limit within the cable. So instead of it being 1,000, let's make it 2,000 and see what the effect of that is. And we've come up with a different structure. And if we check the volume of that, if we remember from previously, it was just over 2. Now the volume is 1.4 times 10 to the 12, so that's in millimeter cubed. So we've reduced by almost a half the volume of the structure by doubling the capacity of those catenary elements. So it's actually an indication of quite how much of the structure was in tension there. And that's the joy of parametric design optimization using Peregrine. You can quickly adjust things like this to answer those sort of what-if questions and get a better feeling for your optimization problem. And other types of structure can be optimized using this. So this is actually obviously an artistic rendering, but again, output from Peregrine for a long span bridge design. You can see how this can be used for long span bridge structures in some of our other webinars. And again, I'll add a link to the description when this goes up on YouTube so that you can take a look at that should you wish. So the next one I'm going to take a look at is load and support mirroring. And mirroring promotes a symmetrical structure as the solution, and also it increases the computational efficiency of Peregrine. So it basically allows twice the problem complexity for the same amount of computational effort. And within Peregrine, we have 3 modes for mirroring. We have a default mode where the load is on one side, the supports are mirrored, and the solution is guaranteed to be symmetrical. We have simultaneous mode where we mirror both the load and the support at the same time, and we have antisymmetric mirroring where the loads and the supports are mirrored in position, but the load direction is unaltered. So yeah, if it's facing the mirror, it will be facing the mirror away from the mirror, sorry, on the other side of it. So as an example, this is one that's been talked about again by Fairclough, this time in an article in the Structural Engineer, and it's an example of a large basement level transfer truss in a multi-story building, and it's 50 meters in span and about 12 meters in depth. There's vertical support at either end that's provided by diaphragm walls, and we have a number of point loads along the top chord and the bottom chord, so the top and the bottom of the design domain when we come to the optimization. And some of these loads, especially on the bottom chord here, are very large in magnitude, so 29 meganewton point loads. And as Fairclough's paper explains, the manually derived solution is one that resembles a Warren truss, linking all the load points, and the weight of this is, you can't really see, it's very small, but just over 460 tons. The paper goes on to perform a layout optimization, followed by a degree of manual rationalization. So we can see this is the basic 463 tons. The optimization, without any finessing, is some 57% lighter than this basic solution, but you can see it's not really constructible. It's very complex. So there was a degree of manual rationalization of this in order to come up with this optimized and simplified design at the bottom, which is some 51% lighter. And this process took a number of hours, if not a couple of days, but it did highlight the fact that the optimization can provide large savings in the material requirements of a structure such as this truss. However, we can now undertake similar ventures using Peregrine and get a rationalized solution along these lines in a number of minutes. So if I jump back into the software, close this example, and we'll take a look at this one here. Just have to zoom out a little and change to the top. Okay, so we can see here on the left hand side, this red area is our design domain. We have loading that you perhaps can't quite see unless I zoom in on the top and bottom chord. And on the right hand side here, we have this blank, but we have mirrored supports and we have mirrored loads too. And if I solve this, it should take a few seconds just to run through, and what we can see here is the outcome from that, which is very much along the lines of the unrationalized solution that was present in Fairclough's paper. So now if we just join the output from that into our geometry optimization, we can see what the effects of being able to move each of these individual nodes is, and try and have a simpler but lighter weight structure as a result of that. So it's just coming through and it's getting towards the end of that optimization. In a second, we can see here, while we're waiting, just what the difference in the volume is going to be. So, okay, so we can see our volume difference is actually about 0.2% lighter. If I zoom out on the right hand side here, we can see a gallery of the two different solutions. On the left here is our original, on the right here is our rationalized one, that we can see actually it's quite a lot nicer, but it's still quite maybe not as simple as we would like. So what I can do is take that geometry optimization output and feed that into a simplification here. So you can see it's working behind the scenes, but what the simplification is doing is effectively saying, I would like to make some aspect of this solution on the right hand side here less complex for a specified allowable increase in volume. So here we're saying actually we can allow up to 50% increase in volume, and what we're going to do is reduce, in this case, the overall complexity of this problem. And it's running through. It's going to take a little while to come in, and then there we go, it's done it now. So we can see at the top here, for just 0.7% increase over this bottom one here, we've actually got a much simpler structure that is eminently more constructible. And we can see the optimum structure here is much like the benchmark in the real problem that was described by Fairclough. Lastly, we've got a couple of minutes left, so we'll talk about structural stabilization. So stabilization in Peregrine uses semi-definite programming to ensure that the structure is linearly stable under the specified loading. And it examines the stability modes and identifies the critical members within that, and then resizes or adds members as needed in order to suppress that buckling up to the desired level that you've put in there. So again, we'll jump into Peregrine and have a look at how that works in practice. So here we have a half wheel problem. So we have supports at the corner, simple supports with a load at the middle. I'll jump in and just solve that. And what we can see on the right hand side here is that's the unstabilized solution, where the volume is 4.6 times 10 to the 2. And this solution here is in unstable equilibrium. So we can imagine at these points here, we could articulate and the entire structure could fall sideways. The stabilization component within Peregrine has then added these elements here for a 3.7% increase in structure volume, and with these 4 bracing elements present here. And the load factor in this case is actually 30, as we can see on the right hand side, left hand side here, sorry. So if I reduce that, we can see actually if our load factor is 10, it's removed these 2 diagonal struts from the problem here, and the volume increase has gone down to 2.5%. And if our load factor is 1, we can see actually these bottom struts are then very much smaller. So we're getting back towards this original problem on the left hand side here. And here's another example from the files that are distributed from the software. Again, there's not really enough time to go into it and solve today, but it's a tower problem with 45-degree loads applied at the top, with the basic layout optimization solution on the left-hand side here. Without stabilization, you can get 2 planar structures, as we can see there, and there's no connection between them. So again, they're both in unstable equilibrium. When we add in the stabilized component in Peregrine, we get the result like we see on the right hand side here, with a 3D stabilized structure. And again, we can go in and further refine that using filtering and as such, in order to get a better, more practical solution from it. It's worth mentioning also that Peregrine will allow you to examine the effects of Euler buckling, either as part of the optimization itself or as a post-processing step. There's, again, not time to go into that here, but we do touch on it again in previous webinars, so please do take a look at our YouTube channel for that. So that's introduced some of the powerful features of Peregrine. Hopefully you've seen what optimization can do for you and how it can drive carbon reduction in construction. Just to summarize, obviously the climate emergency demands that structural engineers do more with less material, and that's very much where optimization can help. Peregrine allows engineers to apply layout optimization techniques to a wide range of conceptual design problems, be they individual trusses or long span bridges, or as we've seen here, stadium roofs. You can download the software from Food for Rhino, and there's a 14-day free trial of the full functionality that comes with it. Finally, just to touch on this for people that want a very quick delve into the world of layout optimization, we've also been involved in the development of a number of apps that are available through layout.com. As the name suggests, Layout Truss is a 2D truss optimization tool, while Bridge includes catenary elements, such as we saw earlier in the presentation, and a number of other features to help explore optimum forms for bridge structures. So it's very much a 2D Peregrine Light web-based application. And a good way to get started. You can play on your phone, tablet, or laptop, or whatever, and see what the influence of load supports and domains and the like are on the optimum form. So as well as visiting our YouTube channel, please do visit those and have a go for yourself. I'm conscious we've run a little bit over, but I will just see if we've got any questions for the Q&A. So yes, we've had one, which is there any published research about this study of grillage holistic design? The answer to that is yes. And what I'll do is, again, I'll put links to it in the description when this goes up on YouTube, so that you can then seek that out for yourself. And yep, that was the only question that we've had today. So given that we're few minutes past 1 o'clock already, I think that's probably time to say goodbye. So thank you for joining us today. Hope you found the presentation useful. Obviously, do give Peregrine a try for yourself. If you visit Food for Rhino, you can download it and try it with the full functionality. And if you have any questions, get in touch with us on info@limitstate.com, and we'll be more than happy to chat with you about them. So that's it for today. Hope you join us for one of our future webinars, but until then, goodbye.